The difference between a toy index and a real one is compression. This is the pattern you'll be able to implement by the end, which builds a compressed index and retrieves the top matches for a query. I'm Professor Pi, teaching search and IR with simple Python. Search systems must serve results fast and read little from disk. Uncompressed postings eat bandwidth and slow queries. Compression shrinks the index and shrinks I/O. That reduces latency and cost. Today, we focus on the essentials. Build a tiny inverted index, turn postings into small numbers, encode those numbers into bytes, then decode them at query time. You will see why each step matters and how the pieces fit together. At a high level, an inverted index maps terms to lists of document identifiers. Compression aims to make those lists take fewer bytes. The usual pattern is twofold. First, replace absolute document identifiers with gaps so numbers get small. Second, encode those small numbers in a compact byte form. This keeps disk reads tiny and helps CPU cache behavior. Our toy corpus uses 4 short documents, so you can watch every transformation. We will build a compact pipeline that shows the whole loop from raw text to hits. The code stays simple. No heavy libraries. You will learn how tokenization, unique postings per document, delta gaps, and variable-byte encoding interact. Seeing the bytes and then decoding them makes the ideas concrete. So the upcoming examples will look familiar rather than mysterious. Now we will build the tiny index. This snippet constructs a tiny inverted index from 4 short documents. It imports regular expressions and a default dictionary to map each term to a list of document identifiers. The variable docs holds small strings keyed by integer IDs to mimic a corpus. For each document, the code lowercases, tokenizes with a simple word regex, removes duplicates via a set, and sorts to keep indexing deterministic. Each term is then appended with the current document ID inside the dictionary inv. The sorted uniqueness per document ensures postings are increasing and contain no duplicates. The printed counts confirm the index was built and provide a quick sanity check on corpus and vocabulary size. Next, we will turn postings into gaps. This example turns a postings list into delta gaps, a classic step before byte-level compression. The function delta takes an increasing list of document IDs and converts it into first ID plus successive differences, which are typically smaller integers. The companion iDelta reconstructs the original list by cumulative summation and will be reused when decoding. The variable t selects the term neural, and g stores its gap-encoded postings computed from the earlier inverted index. Smaller numbers concentrate probability mass and improve downstream coding efficiency because encoders favor short representations for small values. The printed gaps illustrate the transformation and show why delta encoding makes postings friendlier to compression. Next, we will encode those gaps into bytes. This code applies variable-byte encoding to the gap list and counts the resulting bytes. The variable out is a byte array that collects base 128 chunks for each integer, appending low 7-bit groups and marking the final byte of each number by setting the high bit. The loop emits exactly 1 byte for small values, which is common after delta encoding on modest corpora. The variable r computes a raw baseline in bytes, assuming 32-bit integers for all postings across the entire index, setting us up for a global comparison next. The printed length shows how compact one term's gaps become when encoded with variable-byte. Next, we will estimate total compressed size. This snippet estimates total compressed size by counting variable-byte bytes after delta encoding for every term. The helper function E returns the number of base 128 bytes needed to represent one gap, incrementing for each additional 7-bit chunk. The expression B sums that count across delta transformed postings for all terms in the previously built index. The variable R from earlier gives a raw 32-bit baseline, letting us compute a simple percentage reduction. If gaps get smaller, B shrinks further. If doc IDs jump more widely, B grows. The printed reduction quantifies the expected I/O savings from delta plus variable-byte across the whole toy index. Next, we will decode bytes back into postings for a query. This example decodes the previously encoded gaps at query time and reconstructs postings. The variable Q chooses the term neural, whose gaps were already variable-byte encoded into out in an earlier step. Because these tiny gaps each fit in a single byte, decoding here reduces to masking off the high bit to get the 7-bit payloads. The function iDelta then cumulatively sums these gaps to recover the original document IDs for the postings list. On larger data with multi-byte values, you would assemble chunks until the high bit terminator appears before appending a number. The printed hits confirm correct recovery of the postings needed to score results. In a real project, this same flow scales. Replace the 4 documents with a larger corpus, write postings to disk in blocks, and use the same delta plus variable-byte logic per block. At query time, you decode only the needed blocks. That is how large search systems keep latency low while storing millions of documents. Recap: it is an inverted index compressed by delta gaps and variable-byte encoding. Use it when you need to save I/O and reduce query latency on posting lists. One caveat: extreme document ID sparsity hurts gap sizes and makes compression less effective. Next step: scale this exact pipeline to a larger corpus and measure both compressed bytes and query latency to see real gains. If short, practical IR helps, subscribe and watch the IR videos.